Now let me explain to you the definition of kernel of homomorphism. Let f defined from G to G prime be a group homomorphism, that is f of x dot y is same as fx star fy. Then what is kernel of f? Kernel of f is defined as a set of all those elements of G, contain all those elements of G which are mapped to the identity in G prime. That means kernel of f contains only those elements of G that are mapped to the identity element E prime of G. So kernel f is set x belong to G such that fx is called to E prime, the identity in G prime. For example, for you to be more clear, let us consider this example. Define f from set of integers and addition to the group G prime which contains only 1 and minus 1 under the binary operation multiplication. We define fm as 1 if m is even and minus 1 if n is odd. We have seen it earlier that this is a homomorphism. Now let us find out what will be kernel of f here. Kernel of f here is called to set x belong to, set by definition x belong to G such that fx is called to E prime. But what is the identity in G prime? 1 is the identity in G prime. So kernel of f by definition must contain those elements in set such that f of x should be equal to 1, the identity in G prime. And from here we see that only when m is even, then f of m is equal to, that is f of x will be equal to 1. So that means this will be equal to 2 set, because only for x equal to this one 2m, where m is an integer, that means x is an even integer, then only kernel of f of x will be mapped to the identity 1 of G prime. So therefore, this kernel of f in this case will be equal to 2 set, because it will contain all those x belong to set such that x is an even integer. Set of even integer is denoted by 2 set. So kernel of f in this case will be equal to 2 set. So this is a simple example of the kernelity of f. Now let me come to this theorem. F defined from G to G prime is a group homomorphism. Then in that case, f of E is called to E prime. That means the identity E of G will be mapped to the identity E prime of G prime, because E prime denote the identity in G prime and E denotes the identity of G. So this must be true always. So how to prove this one? You take let A belongs to G. A belongs to G. Then AE will be equal to A. Why? Because E is an identity in G. So now here, let us find out what is f of A. F of A will be equal to f of AE, because A is equal to AE. And since f is homomorphism, this must be equal to FA into f of E. Now next, here is as f is a homomorphism. So this implies that FA into FE is equal to f of A. Now, what is the identity in G prime? Because FA is an element of what? FA will be an element of G prime. So now, since E prime is the identity of G prime and FA belongs to G prime, will implies that FA into E prime must be equal to f of A, because E prime is the identity of G prime and FA belongs to G prime, and by definition of identity element in a group, FA into E prime should be equal to FA. So here it will implies that from the last one, FA into FE, FA into f of E, so this is equal to, in place of FA you can replace by FA into E prime. So by cancellation law in the group, so FE is equal to E prime. So this proves that the identity of G will be mapped to the identity of G prime. Now the second one is, we need to show that FA inverse is equal to FA the whole inverse. So for this one again, for any A belongs to G, A inverse also belong to G. Now E being the identity, so A inverse will be equal to E, which is same as A inverse A. Now let us apply F on this one. So f of A inverse is equal to f of E, which is same as f of A inverse A. And this will implies that FA inverse. Why? Because F is homomorphism, so FA inverse will be same as FA into FA inverse. This is called f of E. which is same thing as FA inverse F of A. Now, you can see from here that FA into FA inverse gives you F of E, which is equal to this FA inverse is equal to E prime, because from the first one FE is equal to E prime, which is equal to FA inverse F of A. So what we notice is that now that FA into FA inverse gives you the identity E prime of G prime, because FA and FA inverse are element of G prime. So which means that the inverse, this implies that the inverse of FA is FA inverse. That is, FA, the whole inverse, is equal to FA inverse, because the inverse of FA is usually denoted by FA, the whole inverse. So this proves that FA inverse is equal to FA, the whole inverse. Now let us come to the next theorem, that if f defined from G to G prime is a group homomorphism, which means that fx dot y is fx star fy, then kernel of f must be a normal subgroup of G. So first of all, let us show that kernel of f, let us denote it by k and show that this is a subgroup of G. So here, for this one, you take, let x and y, xy belongs to kernel of f, which is equal to k. So this will implies by definition f of x should be equal to E prime, f of y should be equal to E prime, because kernel of f contain x belong to G such that f of x is equal to E prime. Since xy belong to kernel of f will implies that fx is equal to E prime, fy is equal to E prime. Now let us show that fx, if we can show that xy inverse also, xy inverse belongs to kernel of f, then we can conclude that kernel of f is a subgroup of G. So now let us find what is fxy inverse is equal to fx into f of y inverse, because f is a homomorphism, so fxy inverse can be expressed as fx into fy inverse. And what is f of y inverse? By the second property of that group homomorphism, it is same as fx into f of y, the whole inverse. And this is equal to what? What is fx? It is E prime. And what is fy? It is E prime. So E prime the whole inverse. But the inverse of identity itself, so E prime into E prime, which is equal to E prime. So what we notice is that for xy belong to kernel of f, xy inverse also, f of xy inverse also equal to E prime, which means that xy inverse also is an element of kernel of f. So this implies that kernel of f is a subgroup of G. Now to show that kernel of f, that is kernel of f, which is denoted by k, is normal in G. So you take any element x in k and g in G and show that gx, G inverse belongs to kernel of f. To show that this element belongs to kernel of f, I need to show that f of this one should be equal to E prime. So let us apply f of gx, G inverse, f on this element. By the condition that f is a homomorphism, so we can express it as fg into fx into f of G inverse. Now x belongs to k or x belongs to kernel of f means that f of x should be equal to E prime. So this is equal to f of G into E prime, f of G inverse. Why? Because x belongs to kernel of f will imply that f of x is equal to E prime. E prime being an identity in G prime, fg is an element of G prime, so this will imply that fg into E prime will be fg, so into f of G inverse. So this is equal to f of, you can bring it back here, G inverse. Because f is homomorphism, f of G inverse is same as fg into fg inverse. And these two are, the element G is in G and G inverse is the inverse of this one, so it will give you f of E. But what is f of E? By the first property, it is E prime. By the first property, it is E prime. So you can write here fg into fg inverse, because fg into E prime is equal to fg. fg into fg inverse can be written as f of gg inverse, and this is equal to fe is equal to E prime, because f is a homomorphism. So now you can see that f of gx, G inverse is equal to E prime. So this means that this element is also mapped to the identity E prime of G prime, which means that gx, G inverse belong to kernel of f, and by definition of normal subgroup, it means that this one is a normal subgroup of G. And let us come to the last one, theorem. f is defined from G to G prime is a group homomorphism, then in that case f must be 1 1 if and kernel of f is called E, which means that if f is 1 1 then kernel of f is called E, and conversely kernel of f is called E will imply that f is 1 1. So suppose f is 1 1. Now let me show that kernel of f is E. So let x belong to kernel of f. This will imply that f of x is equal to E prime. But what is E prime? F of x is equal to f of E. And since f is 1 1, it must imply that x is equal to E. So you see that if x belongs to kernel of f, then this x must be exactly equal to the identity, which means that kernel of f will contain only one element, E. Because if you take any arbitrary element x in kernel of f, then we end up that x also equal to E only, as f is 1 1. That's why if fx is equal to fe if f is 1 1 and fx is equal to fe, means that x must be equal to E because of this assumption that f is 1 1. And conversely, suppose kernel of f contained only identity element E, then in this case I need to show that f is 1 1. So you take, let x and y belong to G be such that fx is equal to f of y. So this implies that fx into f of y, the whole inverse, is equal to f of y into f of y, the whole inverse. You multiply on both sides but on the right by fy, the whole inverse. So this will be fx into f of y, the whole inverse. This is equal to E prime, the identity in G prime, because fy the whole inverse is the inverse of this one. So this into its inverse will always be equal to E prime. And here it will implies that fx fy inverse is called E prime. By the second property, fy the whole inverse is same as fy inverse. So now here it implies that f of xy inverse is equal to E prime, which means that xy inverse, because the element xy inverse, why I can write fx into fy inverse as fxy inverse, because f is a homomorphism. So fxy inverse is equal to E prime will implies that this element must belong to kernel of f, because f of this element gives you E prime, and since kernel of f by definition contain all those elements which are mapped to E prime, the identity in G prime. So this implies that xy inverse belongs to kernel of f. But what is kernel of f? I assume that kernel of f is equal to E. So which means that xy inverse must be equal to E. And if you multiply on both sides but on the right as xy inverse y, this is equal to E y. And this will implies that x, now y inverse y will be E, so xe is equal to ey. Ey will be equal to y only, so it will be y, which means that x is equal to y. So now I assume that fx is equal to fy, and I am able to prove that x is equal to y, means that f is 1 1. So this concludes the proof of this theorem.